for homeworks, is it graded based on if you give a full answer, like not if you get the correct answer?
It's written there.
It's written as well.
Look at the homework. It's tell exactly what you do at the top.
I was just making sure. It was because I got a 5, even though I answered more than that correctly. But it's probably I probably didn't put an explanation.
Talk to the TA because he is the one that handles entirely the homework.
So if you circle the right answer, but you don't write anything on the back, it's still correct.
Talk to the TA. He is the one that does it because I don't want to tell you something and then he does something else.
Okay.
All right. Good morning. So just as a reminder, if you have any question about the homework, start with the TA. This is his job. He makes a fortune out of this, and it's a fair distribution of labor. Thank you again for the discussion of last week. I took some action about that. And the action is that the slide today includes a more detailed example with all the steps. This is the same that I'm going to do in class, but you also have it there. And in the homework that will be due when we complete the sequences, there are 2 versions. One is the regular version that you have been doing so far. And one, for each problem, is telling you how to create another 10 problems. So if instead of 1, you need 2 or 3 or 5 or 10, you have them there. If you have any other comment or suggestion to make this more effective or more fun, you tell me, either in class or offline. Some people did it offline and you're very welcome. And we do it. Someone there had a question?
I was just wondering about attendance. Why do people sign up? We don't have to.
So all this is described in online. So I would recommend that you go there and read it. If something is not clear, I will clarify. But there is no point in saying this again one more time. Yes?
Do the extra problems have answers with them too, or are they just problems?
So these are problems. No answer because this is what we have to do for homework. If I put the answer there.
No, but like, is it the regular that's due or the extra that's due?
So go there and look at it because we are not going to assign this any soon. So take a look and then if you want something else, you tell me and I'll try to do it. Great questions? Anything else? All right, so we start a new section today about the sequences, which is another discrete structure. And so I will give you 2 definitions of sequences. The first one is for understanding and manipulating this. But then we will have one which is particularly good when you have to manipulate the sequences with a program. And so we will see this later. So a sequence is a collection of elements like many of the structures we have been using here. This is order. So there will be the first element of the collection, the second, the third, and so on. We put an index. Sometimes we will start from 1, sometimes we will start from 0. There is no difference. You just shift one step forward or backward and you go from one to the other. We will consider even sequences which are infinite. And so there you have an example. The power of 2 is a sequence. 1, 2, 4, 8, 16, 32, and you go on. It's an example of a sequence. Not particularly exciting, I guess. We have a notation, and you see it there. The notation is still with the curly brace that we use for set. So this is very overload. When we write it in that way, we mean a sequence. And that one goes from 1 to infinity. So there is no last element in that sequence. If you want a more concrete example, you have 1 divided 2 to the n, for n that goes from 0 to infinity. And so you see, you can start from 1, you can start from 0. Sometimes when we talk about the sequences, we use things like the sequence is increasing or decreasing, or you can say not increasing or not decreasing. Can be finite. We can talk about the subsequences. We have all the possibilities. So how do we use this one? Here there is an example of a sequence where we want to add all the elements. And we have that notation. There are many pieces. So the strange sign sigma is the S letter of the Greek alphabet for sum. And this sums element of a sequence, so the element of the sequence have an index, and the index is I. A sub I means the ith element of this sequence. And in this case, the sequence goes from I, from M to N. Here we have a concrete example. This is the ith element of the sequence. We take I, multiply by 2, and add 1. And this sequence, I, we make it range from 3 to 5. And so, what is the meaning of this? Is this expression when I is equal 3, plus this expression when I is equal 4, plus this expression when I is equal 5. And we can compute them, and we can find the result. So far, so good? This may remind you a little bit a for loop in your favorite language. Yes?
Are we done with conversion?
No. You do this in calculus, so don't worry. Yes?
Is the sequence technically a set, or do you just use that notation just because?
No. They use the same notation because they run out of parentheses. There are not that many, so. All right, so what is the problem? There is a problem here. Who can tell me what is the problem in this one? The dots. Dot means you have to cooperate with me. If you are passive aggressive, when you put the dots, you can put there anything you want, and how do I argue? I didn't tell you, right? This comes about when it's the computer doing this. Computers are very passive aggressive, so you have to be careful. All right, so the problem is, look, I hate this notation. I want a notation that we call close for, where you have symbols and variables, and you combine them with the kind of operation that you have on a pocket calculator. What do you have on a pocket calculator? Addition, multiplication, subtraction, division, what else? Square root, power, maybe logarithm. No dots. You don't find any dot on a pocket calculator, right? And so the problem is to change this one into one that uses only these elementary operations, no dots. There is a very similar problem where instead of adding, you multiply the things together. We are not going to consider this one, but just for your information, this is a capital Pi, pi for product, sigma for sum. The initial is the same.
So, how do we find the closed forms?
We have some simple cases that we know about. And the first one is that if you add the numbers 0 plus 1 plus 2 plus 3 dot 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 plus n, the result is n times n plus 1 divided by 2. Alright? Later on we are going to prove this one, because we will play with an idea which is called induction. For the time being, you can remember it.
Should we test this in a simple case? This says, look, summation. I that goes from 0 to 5 of I is equal to what? One way to do it is brute force. 1 plus 2, 3. 3 plus 3, 6. 6 plus 4, 10. 10 plus 5, 15. Now, if you have to do this one, you can do it up to 5. If it is 500, it's going to take a little bit of time, right? All right, but here we have this formula that says, look, the sum of this one is 5 times 5 plus 1 divided by 2. What is this one? 15 that you found brute force a second ago. All right? And so we have this formula. We have another formula here that is this one. These are powers. So for example, A can be 2. Let's make an example of this kind. Summation I that goes from 0 to 5, 2 to the I. Yes, thank you. So should we do it brute force first? So for 0 is 1 plus 2 plus 4 plus 8 plus 16 plus 32. You with me? Now, to do this one takes a little bit of time, unless you are smart. What is the sum of this in a very short time? Someone said that, 63. All right, so the formula says, look, this one you can get it by 2 to the 5 plus 1 minus 1 divided 2 minus 1. So 2 to the 5 plus 1 is 64, take away 1, divided 2 take away 1, and this one is 63. All right? And so later on we are going to prove this one. For the time being, I say just believe me. We tested it and it looks fine so far. All right, so we know this one. There are many, many more. If you go to this link, let me see if I can catch the network. Yes. So if I open this one, okay, so if you come here, general manipulation, you see there are dozens or hundreds of these. So, for example, one that we don't look at is I square. I show you summation of I, and I show you summation of A to the I, but I didn't show I square. And I square is that one, and they are difficult to remember. This is why I don't present here. Well, take n, multiply by n plus 1, multiply by 2n plus 1, and divide by 6. And then, of course, you have n cubed, and f to the 4, and f to the p, and you keep going. So, we have all these theorems when we have to do it. In the examples, we will just do the one that you go back to the only two that I'm asking you to remember. All right? And in a second, I'll show you how you get the first. And so I said that the goal is to find a closed form. Closed form. So let's make an example. To I plus 1. I want to compute a closed form of this one. What is a closed form? A form that doesn't have the summation, doesn't have the dot. The only variable that I have here is n. This is the only variable, which is how many
of these terms I add together. And so I will have a function of n where I say, well, I pick n, I subtract 5, I take the square root, I multiply by 7, and we keep doing this one and we get the result. Alright?
So, how do I do this one? First, I split it on the plus. I 0 to n of 2i plus summation I 0 to n of 1. You with me? All right, so what is this one?
So, let's do an example. If you go from 0 to 4, and you add 1, what is the result? 5. Why is 5? Because 0, 1, 2, 3, and 4. Alright? And so this one is n plus 1.
You with me? All right. So now let me massage this one. Here, I take these 2 out because every element here is multiplied by 2. So I can add together without the 2 and multiply by 2 later. So this one will be 2. I'm sorry? Yes, thank you. Summation I 0 to n of I. Yeah? This is our theorem. What is this one? This is n times n plus 1 divided by 2. Yeah? So I have these 2 here and these 2 here I get rid of. And so here I have n plus 1 plus n plus 1. And what is this one? This one is n plus 1 times n plus 1, which is n plus 1 square.
Yeah? Should we test it? So what do we do?
How do we test it? We do summation I that goes from 0 to 4 or 2i plus 1. What is the result of this one? With the formula we just did it, is 4 plus 1 square, right? I'm sorry? I'm out, sorry. And so this one is 25, right? So now let's compute this one. Here I put I, here I put 2i plus 1. I have 0, 1, 2, 3, and 4. What is this one? This is 1. This one is 3, 5, 7, and 9. So 1 and 9 is 10. 3 and 7 is 10. 25. They are the same.
So the fact that the two formula, when I add from 0 to 4, are the same, doesn't mean that this is true. But this give me a little bit of confidence that what I did is right. And if you really want to try from 0 to 7, you do it again, it should be the same, and you do it a few times, and you get some confidence. Alright? If you are lazy and you don't want to do this,
there is a solver online, which is this one. Let me see if I can get there and do it. Summation. So here says the function is 2 times k plus 1, and this one goes from 0 to 5. Oh, I did it from 0 to 4, and here I did it to 5. Sorry. Let me do 4. And here I get the 25 that I computed. You see it? So here, if I say n instead of this one, you get n plus 1 square. You see it?
And so, in the extended homework, I'll give you a dozen or so of these to do. You can do it, you can test it, you can come here and verify that you did it correctly. You don't have to do a dozen. After you do 2 or 3, they are all the same. It's like doing an addition. It's the same concept. After you do 2 or 3, they are all the same. All right? Yes?
The formulas that you said that we have to remember, are those just the three formulas that are on your site?
Yes.
Okay. That's
Just our convention.
I need at least 2 so I can ask you to do something, right?
yeah, because it was very long.
All right. So this is what we do with summations. I think here there is another example
With all the details, and you may try to do it yourself and see whether you are comfortable with it. As far so good? All right, the strings. A string is a sequence whose elements we call characters, even if they are not characters. What is really about the strings is that we use a spatial notation. And so the spatial notation is that when we have a string of elements, the way we write it is each element one after the other, with nothing in between. This indeed is an operation that we don't represent with anything, and we call juxtaposition. There are some languages that do this for functions. Maybe I could pull one here
and show it to you. So I define a function that I call square, and square of x is x times x. All right? Here I can put a parenthesis here if you want the familiar notation, but of course I waste 2 characters for this. So if I load it and I load my square, to compute the square of something I can say square 5, 25.
You see that I don't put any sign between square and 5? This is called juxtaposition. When is this convenient? In this language, the only thing you do is to apply a function to an argument. So it's very convenient that don't use any sign for that. So you don't have to type them. You don't clutter the program with stuff. And so when we work with strings,
We do exactly the same. We write all the elements one after another,
and we call this a juxtaposition. Like when you do the multiplication in algebra, that if you have 2 variables a and b, and you want to consider the product of a and b, what do? You write a, and nearby you write a b. So here we push it. Because we write it like a multiplication, we can use a notation similar to exponentiation. And so this string here that has 2 a's and 3 b's, I write it as a squared b cubed. These are characters. There can be element of any kind. It's just a notation. Alright? So now that I have this notation, I need a notation for an empty string. Why do I need a notation for an empty string? Because there is nothing else to write there, right? And so, if you have a white piece of paper, how do you know whether there is an empty string there or there is nothing? And so I represent it with that one. This is a lowercase Greek letter lambda. Sometimes, or some books, they also use the bigger one, the uppercase. The uppercase is like an A without the crossbar in the middle. All right? Was there a question there? All right. So why alphabets and words are important? A sequence of characters, very often we call it a word, like we do in English, right? In English, what are words? Sequences of characters. So why we care about alphabets and characters and words, particularly in this class? Programming languages. The programming language, the initial representation of the programming language is just a sequence of characters, one after another. And we have a very fancy programs that read the sequence and make sense of it. So, if you have an alphabet, you can make some trivial languages on this alphabet. One is the closure that we denote with this star. These are all the strings, including the empty one, made from the characters of the alphabet. You with me? So, if my alphabet, let me call it A, is made of two characters, small a and small b. What is A star? Who can tell me a few strings that are here? Someone said AA. Yes. Some other? Empty string. This is important. Yes. What else? AB. Very good. B, B, A, B. Any string. You can put any sequence of characters, A's and B, in any way you want, including none. This is A star. Yes?
So does that mean the closure of A is infinite?
So this is a set. So typically we don't call it length. But yes, the number of elements in this set is infinite. There is an infinite number of strings there. Yes?
Is that true as long as you have any values inside of your set?
Yes. An alphabet typically is not empty, because otherwise it doesn't give you any information. All right, we also have this one, A plus. A plus is like A star, but we don't put there the empty string. So these are all the strings except the empty one. The empty string works like a zero when you do just a position, right? If you have a string and the empty string and you just oppose, you concatenate them. What do you get? The non-empty string. The empty string, when you concatenate the just oppose, doesn't do anything. All right, which operation we do? Well, for example, we do the length. What is the length of this string? 5, because there are 5 characters. The length, we use the bar, like we use the bar for cardinality of a set. In some programming language, there is a magic word size, and no matter what is the structure, size gives you this one. So, size in Ruby, for example, size of a set is the cardinality of a set, size of a string is the length of a string. We concatenate the string. So if alpha is the string A squared and beta is the string B cubed, what is alpha beta? Exactly. So here we overload the juxtaposition that we don't even write. And we can use it for string and we can use it for characters. And so, don't get confused. Yes?
Assuming that these are a little different from multi-sets and that order does matter, like
Yes.
ABB is not the same as
Yes.
ABB.
Yes. So, you are right, and let me go back to where we started only half an hour ago. A sequence is an order collection. And so, order means that they have a position. All right, so, what is a language? A language is a set of strings over some alphabet. So, if you talk about the C language, what is the C language? All the string over the alphabet that for the C language is ASCII, that some compiler is happy to compile. You feed it to the compiler and the compiler says yes or no if this is a correct program, well-formed program. The compiler says yes, and this is a string in the language. If the compiler says you forgot a parenthesis or a semicolon or whatever other thing, this is not in the language. Yes?
Does every single language or have the null set, the null string?
No.
So not every language includes the null string.
Right, and not every language includes a null string. Actually,
Except
many practical languages don't. Because the null string, in a sense, it gives you very little information, right? Yes.
and then, but the cardinality always have the null string inside of it?
So the cardinality is the number of elements in a set. So,
Pardon me, the closure. I meant to say closure, I'm sorry.
right, the start closure, yes. The plus closure, no.
Okay. Oh, that's
So, another language is the palindrome over ABC. A string is palindrome if spells the same way backward and forward. So, for example, the single letter A is a palindrome. A, B, B, A is a palindrome. C, B, C is a palindrome. Anything that you spell one way or another. So, this is a language. So, like with every structure, we are able to combine these structures to get a new structure. Sets, maybe you remember, we combined them with what? Union, intersection, difference. And so we do the same with languages. Why is it interesting to do this with languages? This is interesting because when we have to describe a language, sometimes we describe two simple language and then we combine them together with this operation. Very often when you describe the syntax of a language like C, you have some sub-languages like expressions. And you say what is an expression in this language. And then when you talk about a statement, you say, here I just put an expression. And to understand the expression, you don't have to understand the entire language. And so, you do this kind of things. So here, I'll show you 3 operations on languages. So L and M are 2 languages. Let's say one more time. What is a language? Right. Any set of strings over some alphabet. Very good. And so we have these 2 sets of strings. One operation is union. No surprises. These are sets. We do the union of sets, whether they are languages or not. You with me? So this one you know. The other one is the product. This is special for string. This is similar to the Cartesian product. If you do the Cartesian product of two sets, what do you get? You pick one element in one set and one element in the other set, you make them a pair, and this is in the product, Cartesian product. Here we don't call it Cartesian, we call it only product. We take one string in one language, one string in the other, and what do we do? What do we do with string? Juxtapose. And so this is the set of all the juxtaposition of one string in one language and one string in another. Yes?
So is the juxtaposition basically just a concatenation? Like are those
Yes.
interchangeable?
Yes. Yes? So, well, concatenation of languages is called product. We use the word concatenation when we have two strings. The product is the concatenation of every pair of strings, the one in the first, one in the second. You know, call it concatenation wouldn't be a bad idea. But no one calls it concatenation, they call it product. So we just follow the flow. I'm going to do examples, but first I want to present all of them. The final is the closure. Before I told you, look, the closure is every string that you can make with the characters of the alphabet. Now I do it a little better. And I say, look, the closure is the union of products. I just told you what is the union and what is the product. So the closure is the union of products. Which products? You do the product of L with L, L with L with L, L with L with L with L, 4, 5, 6, 7, and you do the union of all these. There is L to the 1 that by analogy is L itself, and L to the 0 that by analogy is the identity of the concatenation, which is the empty string. There is a certain elegance here because all the notions that we have, for example, for multiplication of numbers migrate here to strings. We use the same notation, which is putting one close to the other. We have an operation in multiplication, we call it 1, that when you multiply by 1, you don't change anything. Here we have a value, which is the empty string, that when we concatenate with another string, doesn't change anything. And so once you learn one, by analogy, you almost know the other. Yes?
So that closure involves L to the 0 will include the empty string, even if the language L itself doesn't contain the empty string?
So which language? L, yes.
So L in the
Yes.
example may not contain the empty
Yes.
string, but the
Very good, yes. So let's look at examples of this. Here I pick two sets. The set L has these two strings inside, lambda and A. And the set M has these two strings inside, A and AA. Alright? And so now we do all the operation. We do the union, we do the product, and we do the closure. Alright? So what is the union? We get this one, we get this one already we put it there, so there is nothing to do, and this one. And so the union is lambda A. No surprises. This is the familiar union of sets. The product. What do I have to do the product? I have to pick a string in one, a string in the other one, and juxtapose them. So how do I do to make sure that I don't lose anything? I can do it in this way. Here I put L and here I put M. L has what?
lambda and A, and M has A and AA. You with me? And so I do L with M. So first I put this one, and then I put this one. So here I have lambda A, and here I have AA. Here I have lambda AA, and here I have AAA. All right? So this one is the same as A, and this one is the same as AA. So what do I have in the product? A, AA, AA again. I put it only one because it's a set, and 3 A's. Here it is. Yes?
So when you run two languages through these operations, you're turning it into a set. So and like the same rules of a set apply, like you don't have any repeats, that sort of stuff.
Yes. So a language is a set. A language is a set of words. And the words is a sequence of characters. And when I combine the languages with this operation, I get the new languages, which are sets of words, which are strings of characters. All right, so, yes? It's not the debt. When you do the product, we lose lambda and we gain a cube. Well, because I have to take one string of one and one string of the other. In the other, there is no lambda. So at that point, I will never have an empty string. Yes?
In the products, if there's different characters and they combine, like you do, does it have to be the string from L first?
Yes.
Okay.
Yes. When we do the product, if you look at the definition, the product of languages L and M is the string small l in L and the string small m in M, exactly that thing, in that order. So let's look at the product. Here I have L.
This is the product of L only. Sorry, this is the closure of L only. M doesn't play any role here. So L is this one. All right. So here, let me start with L square, which is a little bit easier to understand. Then we see the extreme cases. What is L square? L square is a string of L followed by a string of L, right? And so what is L square? Do I have lambda there? Yes. Do I have A there? What else do I have? A square. Very good. Let's try L cube. What do I have here? Do I have lambda? Do I have A square? A cube? All right. So what is L1? It's just lambda A. Right? It's like saying, what is 7 to the 1 power? 7 itself. So here I have lambda A. What is L0? Lambda. Fantastic. So now when you do the union of all this, what do you get? This is L star. You get lambda, you get A, you get A square, A cube, and so on. You with me? And so one way to write this one is the way I write here on the notes, which is A to the n, where n is a natural number. So when the natural number is 0, A to the 0 is the empty string, A to the 1 is A to the 2 is A squared, and so on. Yes? One more example.
Yes. A to the 0. If A was a number, it would be 1. And 1 is when you multiply by 1, you don't change anything. When they are string, A to the 0 is the empty string. Because when you juxtapose, doesn't change anything. All right. L contains the string 1 and A. M contains the strings lambda and CC. All right? So K is this problem. L, N squared L. Tell me a few strings that are in K and a few strings that are not. Here I give you some strings. You can pick this one and tell me which one are in K and which one are not. Oh, sorry, here I wanted to put the power, but I guess I mistyped it. 1 1 is in K, yes. ACCA, yes. Is a 1A in K? Yes. Is A to C, and A again in K? Is this one here that unfortunately is poorly written, but this means A times C, A again. Yes, no, maybe? No. Too many C's, right? Yes. 4 C's is it? And so this one, where you have 1, 4 C's and 1, this one is there. All right. So, let's review what we have been done up to this point. All right?
We cover a lot of material. We have defined a sequence. A sequence is an ordered collection. Order means that when we pick 2 elements, we know which one comes first, or which one is number 7 and which one is number 12. And because they have a position, of course, we can have repetition. We learn some notation for that one. And now we are looking at applications of these sequences. One is for summations. We define the notation for summation. That sigma, what are all the little pieces that are there? What is the meaning? And we said when you have a summation, the problem is to find a closed form. In the summations often have dots. The first line is telling you that the definition includes dots. We want to get rid of the dots. How do we do? Well, we have some particular cases like the summation of I or the summation of A to the I, or we sorry, the summation of I squared. When we have something more complicated, we break it and we massage it to go back to those cases. We have 2 examples here.
One where we are doing a 2 times I plus 1. To practice, you could do 7 times I take away 4, or something like that. The mechanics are entirely the same. In fact, you could just use A and B and find the general form. And then we saw another one is here. There are all the steps. I haven't done it, but it's 2 to the I plus 1. There are many others that we don't know how to solve because I only gave you 2 theorems. If instead of 2 I give you a dozen, we can make a much more rich example. But we don't because I didn't give you then the theorem that at the end allows you to produce the result.
Summations. Strings.
We said what is a string. A string is a sequence of elements that we call characters. For example, there is a recent very important branch of computer science that is concerned with operation on strings where the element of the strings are the nucleotide of the DNA. So this is an alphabet where you have 4 letters, and you want to find whether this is there, is repeated, you put something or you took something, and in this way you can find diseases, discover who is the father or sibling of whom, and things of this kind. All these are manipulation of strings. Some algorithms are very fancy. And so strings are sequences of elements that we call characters. They don't really have to be characters of an alphabet, like the English or whatever is your alphabet. We have a notation, juxtaposition. We write the things one near the other, exactly how we write the words in the English alphabet, where these are sequences of letters of the English alphabet that we write one near the other. We have a notation like multiplication, where you use exponentiation. We said that a language is a set of strings. You put whatever strings you care about in your language. On one extreme, you put nothing there. That's not very interesting language. On the other extreme, you put everything there. Again, not a very interesting language. When we have languages, we do operations, union, product, and closure. These are very convenient when you have to describe a more complicated language. You say, this complicated language is the union of these 2 simpler languages, or is the product of these 2 simpler languages. And so the 2 languages are easier to understand than the big one. So that's it. Should we take our 10 minutes break? All right.